In section 4.3, we're going to take what we learned in 4.1 and 2 about exponential growth and decay, and we're going to learn about a new constant, Euler's number. It's a number similar to pi, so it's a constant number, and it's represented by the letter E. And we're going to use Euler's number to graph exponential growth and decay, and also to calculate continuously compounded interest. So we've got the natural base of E. You can find that on your calculator. You'll see there's an E button. And also, it's approximately 2.72. And what Euler figured out was that if you take a look at this item, we have A is equal to principal times 1 plus R divided by n to the nt power. And what he was looking for is, all right, rate changes and time changes, principal changes, but if I just look at a part of this function, 1 plus 1 over n to the n power. And what he found is that as n approaches infinity, then this whole thing will approach 2.72, which is Euler's number. So what it allows us to do is it allows us then to compound at the infinite rate, which is what we call continuously compounded interest. The type of problem we might use to solve this would be this one. We've got a formula that involves the letter E, right? Given the length of a shark based on its age. Okay, so L would be the length of the shark, T is the age of the shark, and this is a formula that will allow us to find the length based on knowing the age of the shark. So 2.71828, blah, blah, blah. This is Euler's number. This is essentially what it equals. Okay, and so it's 1 plus 1 over n to the n power. As n approaches infinity, E becomes 2.718. So if we're going to continuously compound, then we can go ahead and use Euler's number to do that. So we're going to work with the letter E, and at first we're going to look at simplifying expressions that have E in it. And in this case, E doesn't function any different than any other variable. So if I have e to the third times e to the fourth, it becomes e to the seventh. I add the exponents. This would become 3e to the 1 minus x power, because we subtract the exponents when we're dividing. So the properties of exponents don't change just because the base becomes e. If I wanted to go ahead and evaluate these, I'd pull out a calculator. And you see I have an E button here. So if I do E to the third power, it's 20.089 basically. So if I do E to the negative 2/5 power, I'm going to use another calculator that I have online. And you see I did E to the negative 2 divided by 5 power, and it's 0.67. So this is mostly just plugging into your calculator. You notice that I had to put parentheses around the negative 2 divided by 5 in order to correctly put this into the calculator. So go ahead and practice some problems. We've got problems 4, 8, 12, 20, and 24. Go ahead and do those to get some practice working with E. They're very simple, and it relies on properties of exponents that you've already learned. So when we talk about graphing, again, this is not going to be anything new. We just now have E as the base of a power. Okay, so you can see that E being 2.72, it's greater than 1. So if I just do y is equal to e to the x power, it's exponential growth. If I have y is equal to e to the negative x power, that's really the same as y is equal to 1 over e to the x power. This is a fraction. It's a little more than 1/2 1 over e. So when I take this to the x power, then it's going to become decay. All right, but the methodology for graphing is no different than what we've already learned. So this one is going to be, right, a decay function because it's the negative 2 power. It's the same as y is equal to 1 over e to the 2x power. If I do an input-output table, I'm going to use -1, 0, and 1. Right? If I have -1, that's going to be e to the 2, right, to the negative 1 over e to the negative 2x power. Is basically going to be e squared. That's going to be approximately 5. If I have 0, 2 times 0 is 0, 1 over 1 is going to be 1. And to the first power, it's going to be basically e squared. It's going to be about 1/5. About. Okay, so when I graph -1 is at 5, 1, 2, 3, 4, 5, 1, 1/5. And remember, I'm pretty familiar with these, so I'm estimating these values. You'd go ahead and use a calculator, and you could get very accurate values. Okay, but I really want you to get the idea that just because the base of the power is e, it doesn't mean anything changed in terms of how we graph these things. It's the same. Okay, in this case, I want to identify h and k. H is equal to -1. K is equal to -3. Then I'm going to graph this. In fact, I already have what without h and k, so I'm going to take those parts off. Y is equal to e to the -2x power. Well, if you notice, that's what I just graphed. So I'm going to take this graph that I already had, 1, 2, 3, 4, 5, 1/5, and now I'm going to use h and k. So again, h is a horizontal shift. I move 1 to the left. K is a vertical shift. I move down 3. So I go 1 to the left and down 1, 2, 3. That's this point. 1 to the left and down 1, 2, 3. That's this point. And then 1 to the left and down 1, 2, 3. That's this point. And here's my new function. And because I have a value of k that's not 0, that also means my asymptote moved. So my asymptote is now at y is equal to -3. Okay, so this is again translating my function, my exponential function. Go ahead and practice that again. You should already know how to do this. Try 43 and 49. And now we're going to talk about continuously compounded interest. So now we have a new formula. And the key for you is, when do you use this formula? When interest is being compounded continuously. So if our interest is being compounded monthly, daily, annually, quarterly, we use the other formula that we learned before, right? That is going to be A is equal to principal times 1 plus R divided by N to the NT power. And if we're continuous, then we use PERT, principal times e to the RT power, because e has come in to replace 1 plus 1 over n to the n power. So you notice n is gone, but we put r and t into this, and we're ready to go. So in this case, my account balance would be equal to my principal, $800, times e to the RT power. Well, my rate is 0.0265, and my time is 12.5 years. Okay, so again, I'm going to use a calculator for this. So if I have E, and I'm going to take it to the 0.0265 times 12.5 power, I get this value, times 800. So it becomes 1,114.17. 1114.17. Right, this was dollars as well. Okay, so again, you'll notice that when let's go back and take a look at how I plugged that in. You see, I put parentheses. I'm sorry, that was the previous calculation. I put parentheses around this, right? I wanted to do e to the 0.0265 times 12.5 power. So again, when I'm doing my exponent, I have to put parentheses around it, because what I don't want to do is take e to the 0.0265 power and then multiply it by 12.5. Okay, so just make sure you're using your calculator correctly. You shouldn't have any trouble. So I've gone ahead and I've taken this equation. It deals with the length of the shark in centimeters. That's important to notice, in centimeters, based on the age of the shark, and I can use this formula. So the first thing they asked me to do is graph the model. I've gone ahead and done this with my online graphing calculator, and here it is. So this is the graph of this function. Okay, and you can see that this is, right, it's an exponential decay model, right? It's inverted. So you see it's the values, absolute values are very large here. It's vertical here on the left side of the graph. It's flat as we go out. That makes sense because I'm taking e to a negative power, right? So it's a decay function. And then they want me to find out what's the length of the shark at age 3. So if I pop in here, 175.2 centimeters. Okay? So I know that the length of the shark is 175.2 centimeters at that age. Okay, so that's the end of section 4.3.